we are going to move on to topics related to multimedia applications. That is, for example, voice calls, video, conferencing, TV over the internet. And we'll see that for networks to support such applications, they need to sometimes provide better performance than our normal networks, because many multimedia applications require good performance in terms of delay, low jitter, sometimes high throughput. So we need sometimes different network mechanisms to support these multimedia applications and other applications. Sometimes we need to give priority to voice applications, to voice calls, so that the voice call is good quality while the, for example, web browsing can be background traffic. So to differentiate the priority of different traffic. So we introduce the concept of quality of service, giving some application one priority and another application a different priority is the main part of quality of service. And some multimedia applications, especially streaming-based applications, involve multiple receivers. You listen to internet radio. There's one radio station. There are multiple people that may be listening to that radio station. So we'll introduce the concept of multicast, which allows sending from one source to multiple receivers. And then the next topic, we'll look at different multimedia applications. So we'll first go through multicast and more generally the different delivery mechanisms available, and then go through two different examples of how to provide quality of service. Let's first look at the very basic addressing and delivery mechanisms in any network. How do we deliver packets in a network? Whether it's a layer 2 network like our LAN or a layer 3 network like the internet across the globe. We've got four basic types of delivery mechanisms: Unicast, broadcast, multicast, and anycast. We know about Unicast, that's our normal delivery mechanism, one-to-one. Broadcast we've spoke about, you may have heard of multicast, you may not have heard of anycast. We'll describe all four of them. And then we'll go into some depth about multicast. Unicast is our normal delivery mechanism. I want to send a packet from my laptop to some destination computer. It's a one-to-one mapping of, or a one-to-one association between address and host. That is, I send a packet and I set some destination address. That destination address corresponds to one host in the network. So if this host computer has address 10.10.1.200, when my source creates a packet to send, it sets the destination address to 10.10.1.200. That IP address identifies one computer in the internet. So we'd say it's quite simply a one-to-one association between the destination address and the host on the network. A host sends a packet to some destination address X. That packet should be delivered to that destination, and only host X will process that packet. We be careful, we say only host X will process that packet. Other hosts may receive that packet, but they should not process it. And in layer 2, we'll use IP as the example of a layer 3 network, and Ethernet as the example of a layer 2 network. So these mechanisms we talk about are general to different networks. In layer 3 networks, in the internet protocol, IP unicast, quite simply, we create an IP datagram, set the destination address to some IP address, where that IP address is of a format that identifies an individual host. You already know that there are other types of or there are particular types of IP addresses that identify multiple hosts, broadcast addresses, for example. But here's an address that 125.70.16.3 identifies a single host. We set the destination address to that IP address, send it through the internet, and it should be delivered to just that host. Same in layer 2 in Ethernet. A frame, an Ethernet frame, we set the destination address to some MAC address of the host we want to send to, and send the frame. Be careful in that we say that the packet or frame should be delivered to the destination and only processed by that destination. In some networks, the packet may be delivered to other hosts. Consider wireless LAN. Our access point, we have multiple clients associated with that access point, all within range. They have addresses. So each client has a MAC address. We don't care what they are, except that they should be different. So each client has a MAC address. The access point also has a MAC address, but let's say the access point is the source. If we're using Unicast, the access point has a frame, an Ethernet frame, actually a wireless LAN frame. Remember back to wireless LAN that we have, we have multiple addresses, 3 addresses in the frame. The one we care about is the destination address. The destination, if we want to send to client 1, is set to the MAC address of client 1. And we transmit this frame across the wireless LAN. But remember, in wireless LAN, our transmissions are broadcast. That is, when I transmit a frame on my laptop, the radio signal is received by all stations within range. So I transmit some signal. Everyone within range of the access point receives that signal. And effectively, everyone, client 1, 2, and 3, receive that frame. But because this is Unicast, each client looks at the frame, they look at the destination address, and if it matches their address, then they process that frame. If not, they discard the frame. So when we say Unicast, the packet or frame should be delivered to the destination host and only processed by that destination host. In some mechanisms, when we deliver, even using Unicast, we can think from the physical layer level, it's broadcast. Everyone receives a copy, but inside the receiver, the Mac implementation looks at the destination address in the received frame, checks, does this match my address? Yes. This one will process the frame. That is, the MAC layer will process it, send it up to the IP layer, and so on. It'll be received by the application at client 1. This one will also receive the signal, sees the destination address in the frame. It doesn't match its own destination address, so discards that frame. Yep.
If you use a security wireless such as WPA or WEP, does the receiver that is not the desired receiver of the frame can read the data inside?
If you use security inside the frame, some encryption, if this is our frame, we have a header. One field in the header is the destination address. Then we have data. The data is encrypted. The data is encrypted. If we use encryption, the header is not encrypted. The destination address is in the header. So still, access point sends an encrypted frame to C1. Only the data inside that frame is encrypted. Access point sends the frame. Because in wireless transmission it's a broadcast medium, we send a signal, everyone within range receives that signal. So effectively everyone receives that frame at the physical layer level, but they check the destination address again because the destination address is not encrypted, it's only the data that would be encrypted. C1 receives this frame, checks, it's to me, take the data, and if it was encrypted would need to decrypt that. C2 receives the frame, checks, it's not to me, discard that. If it was programmed to do something different, it could try to look at the data, but the data would be encrypted in that case.
So only the access point and the receiver can read?
Only, if we encrypt the data, only the stations that know the key to decrypt it can read that data. Even though your mobile phone sends to an access point using encryption, so it's slightly off topic, but if you send to an access point and if you've encrypted that data, my laptop can receive it, and I could turn on configure my laptop to intercept and receive, not a problem, but I couldn't read the data because it's encrypted.
And if your laptop connects to the same access point, can you read the data?
No. I need to know the secret key that is known by your mobile phone and the access point. If I configured the access point, I would know what the secret was.
Key is unique for each station, right?
The secret key is,
The access point key to each.
for example, when you connect to a secure network, you need to provide a password. That forms a secret. So in general, with encryption over a wireless link, anyone can receive the frame, same here. If C1 is communicating with the access point, C2 and C3 can still receive the frame, but with encryption, to make sure that C2 and C3 cannot read the data, we encrypt that data, such that you need some special key, such as a password, to be able to decrypt and see it. So we're talking about Unicast, which is sending to one destination. My point here is that with some networks, we may use, for example, broadcast at the physical layer to deliver that packet to an individual host. Another way we could visualize what's happening there at the receiver, if we draw the stack at C1, have the physical layer, data link, IP, transport, application, and at C2, both of the C1 and C2 receive that frame that was sent by the access point. So we can think that the physical layer receives the signal, processes the signal and sees it's a frame, passes the frame to the data link layer. The data link layer is where the addressing is performed in wireless LAN, in a layer 2 network. That is, data link layer now has the frame, this. Inside the frame header is the destination address. It checks at the data link layer, does the destination address match my address? C1, yes it does. Process the data, send it to the IP layer, send it up, and the data is received. C2 receives a frame at the data link layer, checks the destination address, does the destination in the frame match my address? No. Discard the frame. Do not process it any further. That's the point here. Both receive the frame, only one processes it. So that's an example for a layer 2 network. Of course, we also have Unicast in layer 3 IP networks. So that's the simplest delivery mechanism. Send to one individual host on a network, Unicast. What about the next approach, broadcast? And we know something about how broadcast works. We send to every host in a network. We need to define what the network is. So we have now a one-to-many association between address and hosts. That is, we have one address that represents many hosts. In Unicast, it's a one-to-one association. We have one address, this 001731AA BBCC, that identifies or that associates with a single host in the network. With broadcast, and in fact with the subsequent techniques, broadcast, multicast, anycast, we have a one-to-many association. One address, a broadcast address, like a broadcast address with the 255 or the all-F address for the Mac layer, identifies many hosts in the network. And many in broadcast means every host. In the multicast and anycast, it'll be a one-to-many association, but many will be defined differently. I never remember. So we know of examples of broadcast address in both layer 2 and layer 3 networks. In layer 3 networks, in the internet, we have two different types of broadcast address. We have a directed broadcast address and a local broadcast address. A directed broadcast address is that we set the host portion of the address to all ones in binary. So for example, if my host was 192.168.1.2/24, the subnet mask tells us that the network portion is 192.168.1, the host portion is .2. That is the first 24 bits of the network portion. Then the corresponding directed broadcast address is 192.168.1.255, where the host portion is set to all ones in binary. This address, 192.168.1.255, is a single address which represents all hosts on the network 192.168.1, 1.0. So it's a one-to-many association from one address to all hosts on the network. So when we send an IP packet where this address, 192.168.1.255, is the destination address, then the network should deliver a copy of that packet to all hosts or all IP devices on that network. Broadcast. Although not listed here, we also have a local broadcast address where we have in binary 32 ones. In dotted decimal, 255, 255, 255, 255. Again, deliver a packet sent to that destination address to all devices on the network, on the subnet. Except that's the difference between the two is that the 255 address is sent to all hosts on your current subnet. This is called the directed broadcast, which is sent to all hosts on a particular subnet. But both examples of layer 3 broadcast addresses. At the MAC layer, or at the data link layer, layer 2, we also have broadcast addresses. Again, it's by all ones, but we just have a different address format. We have 48 ones in binary. Convert to hexadecimal, we get this all Fs address using our MAC address. Let's give an example of how that could be implemented.
Teacher,
Yep.
if we broadcast in layer 2 using
In layer 2 broadcast, we inside one subnet, inside one IP subnet. Let's see with an example to illustrate some of those concepts. We'll draw two IP subnets with some hosts, the square ones, a router, a switch, so some 3 hosts. Let's give some names to them. 1, 2, 3. Router A. And an access point. And some other hosts. Four, 5, 6. So in this case, we have 2 IP subnets. The left-hand side, where we have 3 hosts, hosts 1, 2, and 3, connected via Ethernet cables to a switch, a LAN switch, which is also connected to a router, router A. So this is one subnet. And we sometimes draw a subnet as some cloud and hide the details, the internals of that subnet. And here's a second IP subnet. I'm going to change the address of the router to be 7 and call this first subnet subnet A and the second one B, so I can refer to them. So each host on subnet A will have an IP address, and similar on subnet B. And instead of writing the full IP addresses, I'll just use abbreviated ones where I use the subnet name. This one has the IP address A.1. And this host, host 2 on subnet A, let's call it A.2 and A.3. That's the IP address of that host. And similar on subnet B, we have B.4, B.5, and B.6. Where, for example, B may be 192.168.2 and A may be 192.168.1. So just save me writing them down. Similar, the router has an IP address on both subnets. Let's call it here on this side is A.7 and on this side would be B.7. A router has an IP address for each of the subnets it connects to. The devices also have MAC addresses. So there's the MAC address. Let's call this one MAC1, MAC2, MAC3. Our wireless hosts also have MAC addresses, MAC4, MAC5, MAC6. Our router, does it have MAC addresses? Does it have layer 2 addresses? Yes, it does. Again, each interface has an address. What am I going to call them? MAC7 and this one MAC8. Any more MAC addresses in this network? What about our access point? Yes, we have the we have a MAC address on the wireless LAN access point. Remember, with the wireless LAN frame, we set the MAC address. We have 3 addresses in the frame: original source, final destination, access point address. So it also has a MAC address. But for simplicity, I'm going to hide that, because when we send a frame from MAC 8 to MAC 5 via the access point, we send it via Ethernet to the access point, but when we send that across the Ethernet LAN, the destination address is not the access point, it's MAC 5. That is, if the router wants to send to host 5, it would send an Ethernet frame with the source equal to MAC 8 and the destination equal to MAC 5. If the router wants to send to host 5, it would go to the access point, and the access point would send in,
Does the solution have MAC address?
Let's finish on the wireless side, on subnet B.
And if an access point has 4 ports, which does it have 4 MAC address for each port?
Let's see what happens to send a packet from 7 to 5, and we'll answer that question once we see that, because look at the addresses that are important here. Yes, we know an access point has a MAC address. From the host who's sending this data from router 7 to host 5, they want to send one IP datagram from here to here. The Ethernet frame that is sent, that is created by host, or from router 7, has a source MAC address of MAC 8 and a destination MAC address of the MAC address for the host it wants to send to. How does it get that MAC address? Using ARP, Address Resolution Protocol. That is, if at the IP layer we want to send to B.5, we use ARP and we find the MAC address for IP address B.5 is MAC 5. So the Ethernet frame sent from the router, source address MAC 8, destination MAC 5. Sends it across the cable that it's attached to. It's received not by MAC 5 but by the access point. The access point sees that it needs to send to MAC 5, so it creates a wireless LAN frame. Source address is MAC 8, the original source. Destination is MAC 5. From that perspective, we can think, well, the access point is just forwarding this frame across the LAN. It's just a bridge that is not changing the addresses. We've got the same data, different frame structure, but the same source, MAC 8, and the same destination, MAC 5. But we know also wireless LAN has a third address, which is the access point address. If we go back to our topic on wireless LAN, there are 3 addresses in the wireless LAN frame: source, destination, as well as the access point address. So there's a third address in here. But if we look at the endpoint's perspective, source MAC 8, destination MAC 5. When this host receives this wireless LAN frame, it is the destination, MAC 5, and it knows who the source is on that IP subnet. So yes, there's a MAC address for the access point, but in terms of communications across that subnet, the most important addresses are the addresses of the individual hosts. Do we need an address on the switch? Well, it's the same issue. The switch just forwards that frame through the subnet. Host 1 wants to send to the host 3, source MAC address MAC 1, destination MAC 3. The switch doesn't need a MAC address to handle this. Host 1 just sends to the switch across the cable. The switch receives this frame and notices that the destination is MAC 3, and when the switch was turned on and the host 3 was turned on, they did some negotiation, and host 3 told it that MAC 3 is connected via this cable. So when we send a frame to the switch looks at the destination address. If the destination equals MAC 3, the switch then knows, or is configured to know, to reach MAC 3 I send on this cable, or on this port on the switch. Our switch has multiple ports. If the destination was MAC 2, it would send on this port to host 2, and MAC 7. So from that perspective, we don't need MAC addresses for the switch. And I'm not going to worry about the MAC address for the access point, because it's effectively the same type of device. Does that answer your questions? Okay. Now, some switches may have MAC addresses because sometimes you can manage the device. You can log on to the device and change the configuration, but that's different. That's not about the switch forwarding, that's about you configuring the device. Same as an access point can have an IP address. It doesn't need one, but often they are given an IP address so that you can connect to that access point and change the configuration. So back to our problem of broadcast. Here's our example internet, 2 subnets. Let's do a broadcast from host 1 where host 1 has a IP datagram has some data, an IP header, and to make some space, destination address in the IP header is how are we going to call it broadcast? B.255, where B is our network portion. For example, 192.168.2.255, which means I want to send this IP datagram to everyone, is the broadcast address, on subnet B, this subnet. So this is a directed broadcast. Host 1 wants to send to everyone on this subnet. So it creates an IP datagram, sets the IP address, the destination IP address, to be the directed broadcast address for this subnet, subnet B. Where does it send? What does it do next? Host 1. If you cannot see, then you have to sit over this side, but host 1, what does it do now? It has an IP datagram, destination, broadcast in subnet B. What's it do? What do you think it's going to do? Host 1 wants to send a datagram to everyone on network B. First, where does it send this IP datagram to? Where does it send the datagram to? The goal is to get this one datagram, a copy of it, to everyone on this subnet, a broadcast on that second subnet. What happens next? What do you think is going to happen next? It wants to broadcast on subnet B, so it's not going to broadcast on subnet A. Or it doesn't need to. I guess it could, but it doesn't need to. Where should host 1 send this packet, this IP datagram? It's going to send to the switch. He's only got a connection to the switch. It's going to go to the switch, and then where? 2, 3, 7, or all of them? 7. The router. So this is not about broadcast, this is just about routing. That is, we have a packet, destination address is another subnet. Okay? Host 1 is on subnet A, destination is on subnet B. The fact that it's broadcast doesn't really matter here. To reach subnet B, look in our routing table, which we don't have here, but look in our routing table, which should tell us send to router 7. So we put it inside an Ethernet frame. So this is the Ethernet header, and set the destination address of that Ethernet frame to be MAC 7. That is the MAC address of the router. How do we know that? Because we know the IP address of the router from the routing table, and we can, given that IP address, we can look up the MAC address of the router using ARP, Address Resolution Protocol. So this is at host 1. Create an Ethernet frame, destination is MAC 7, source is MAC 1. Send it to the switch. Switch knows to reach MAC 7, send on this output port. And therefore, the router receives this Ethernet frame. That was Unicast. That was Unicast across the LAN from here using layer 2 technology. Destination address was MAC 7. It identifies just a single host. Send it to the router. Router, because it's reached the destination from layer 2 perspective, it removes the header, processes the data inside, and realizes, okay, the destination of the IP datagram is B.255. So now the router has this datagram, B.255. The router knows it's attached to subnet B. What does it do next? So router 7 has this IP datagram. Destination is the broadcast of for subnet B. What does the router do now? Forward to access point. Okay, well that's almost obvious because it's only got one cable, but good. What's the destination address? All of them, and more specifically, the destination address of the Ethernet frame will be? All ones, all F, yeah. So this address. Router 7 has this IP datagram. Let's draw it here. Destined to B255. That is the broadcast address for this subnet. Once it realises it's a broadcast to the subnet it's attached to, it puts it inside an Ethernet frame and sets the destination to be the all F's address, which is the special broadcast address for Ethernet, this address. How do we broadcast inside this subnet? Well, even though we want to reach everyone, we only have one cable coming out of the router on this subnet, so we send it to the access point. The access point receives it. It sees the destination is, or the all F's address. It needs to send to everyone. So now it broadcasts to everyone that it's associated with the address, with the access point. How do we do that on wireless LAN? How many times do we have to send a wireless LAN frame? We want to reach now clients 4, 5, and 6. Access point has a frame. It needs to send it across wireless LAN. What does the access point do? How many frames does it send?
One.
It can send just one frame. Because with wireless, it's broadcast. that is the physical layer's broadcast. We create one frame, which is just this one. Destination, except our header changed to a wireless LAN header. Destination address is still the all F's address. We transmit this one frame across wireless LAN using the DCF mechanism, except it's no longer the original DCF. There's a slight difference. But we back off, transmit a frame. When host 6 receives this frame, it checks the destination address. The received frame has destination address all F's, all 1s in binary. Host 6 MAC address is MAC 6. It doesn't match, but because it realizes this is a special destination address, it accepts that frame. In the example we had at the start, a client that receives a frame checks, does the MAC address of the destination match mine? If so, process. If not, don't process. It's slightly more than that. Does the MAC address match mine, or is it a broadcast address? In this case, destination is the broadcast address. MAC 6, host 6 receives that, checks, sees it's the broadcast address, and then therefore processes the data, accepts the data. Removes the header, looks at the destination IP address, sees that matches, processes the data, and has received the data. At the same time, that happened with host 5. Because we transmit this frame, everyone within range receives it. Host 5 receives, does the same thing, processes the data and has received the data, and same with host 4. So one wireless transmission, all 3 hosts associated with that access point receive that frame. And we've broadcast it through the subnet now. Everyone has received a copy. 4, 5 and 6 has a copy, as does the router, in fact. So broadcast is easy in a wireless network. Just send once, because broadcast at the physical layer, wireless at the physical layer is broadcast. We just send the frame once, but just set the address of the destination to be that special address. Everyone should receive and process. The difference when we broadcast in wireless LAN is that we don't send back an ACK. Why? If we're getting in detail here, but if we go back, we do our back off, diffs, back off at the access point, and then transmit the data. That's what the access point did. 6, 5 and 4 receive that. How would we deal with an acknowledgement? 4 receives the data if it sends back an acknowledgement, and then 5 also receives the data at the same time if it needs to send an acknowledgement, and also 6 needs to send an ACK. Who sends first? It's not easy to organise. That is, if we have acknowledgements, 4, 5 and 6 need to send back an ACK to that same piece of data. A, that's hard to organise, which one transmits first, and B, it becomes inefficient because there's a lot of acknowledgements sent. Let's put 50 nodes in the network, not just 3. I send one broadcast data frame, I receive 50 acknowledgements. That problem is called the broadcast storm problem. I'm not sure if it's said here or somewhere. We get a storm of acknowledgements back if we have such an acknowledgement scheme. So normally when we broadcast data, we don't expect ACKs back. So we've seen an example of how we send a packet to a directed broadcast IP address. In reality, that may not work, because in reality, routers may be configured not to accept this broadcast packet. If in the internet we allowed such a behaviour, it means with my laptop, I could send a directed broadcast address to Facebook's network so that all the hosts on Facebook's network in the US receive a copy. If I knew its directed broadcast address, I would send it via the routers in the internet and it would reach to the router in Facebook's network. Every computer in Facebook's offices would receive a copy. That's insecure in that I can flood other people's networks with packets very easily. So in practice, this router may receive this frame, see the destination address, and may say, no, I will not forward this broadcast on for security reasons. But in theory, that's how it would work. One more example. I will not draw it. Router 7 wants to send to everyone on its address, on its subnet. Router 7 creates a frame, an IP datagram. Destination is the 255.255 address. That is the local broadcast address. Router 7 wants to send to everyone on this subnet. What happens? Again, create a MAC frame, set the destination MAC address to be all F's address. So put this into a MAC frame where the destination is the broadcast at layer 2. Send to the switch, because that's the only device we're connected to from the router's perspective. The switch receives this frame where the destination is the all F's address. When the switch receives that, it sends a copy to everyone that's attached to it, except where it received from. So the switch receives one frame, makes copies and sends to everyone that's attached. That's an easy way to do a broadcast on the LAN. The switch performs the broadcast for us. That is, it copies the frames and sends to everyone who's attached. As a result, 1, 2, and 3 will receive a copy. Go ahead.
We can send remote SSH to broadcast. Can we send it?
Can send
remote request?
You mean that can he broadcast to SSH to all computers? Remote to all computers?
can we? The question is, can, for example, SSH, the application that allows you to remotely log into a computer, can we remotely log into many computers? Well, no. The application protocol needs to support broadcast if we want to use it. If I want to log into all computers at the same time, well, that would mean I'd need many different windows open to be able to type something separately into the different computers. So the SSH protocol does not support a broadcast like that. Ping is another application protocol, and that does support a broadcast. I think with ping there's a -B option where you can ping broadcast. So on a host, normally you ping a particular computer, you can ping the broadcast address, where the aim is to send to everyone on the subnet. So some applications support broadcasts, some, where it doesn't make sense, do not. But the network supports the broadcast mechanism. Whether the application implements that, it's a different thing. It depends on what the application does.
He asked because he wants to pay something in your lab tomorrow.
You can try SSH to multiple computers, but basically what remote login does is it gives you a terminal on another computer. Giving you a terminal on multiple computers at the same time doesn't make sense, because if you type something in, you could write your own program that does that, that sends a command to multiple computers. That's a different thing. Let's say I want to send a command to all computers in my network at the same time. So I type in one command, press enter, and that command is executed on every computer in the network. That's possible. You'd have to write your own protocol to do that, but that's possible. And you could do it two ways. You could do it using broadcast, where the command is sent to the switch and then using the broadcast address. But we can perform broadcast using Unicast as well. How? Simple. Let's say we didn't have the broadcast address of all Fs, but we had this destination address of the 255. That is, the router wants to send to 1, 2, and 3. Having broadcast is efficient because we send to the switch just one copy. The switch makes copies and sends to the destination. We've sent 1 frame plus another 3 frames with broadcast. To get the same result, we could use Unicast. Simply, the router sends one copy using Unicast to 1, sends another copy to 3, and another copy to 2. Again, same result. 1, 2, and 3 have received a copy. So we can emulate broadcast using Unicast. Same result in that everyone receives a copy, but less efficient. We've sent from the router 3 frames to the switch, plus 1 to the destination. With broadcast, we send 1 frame to the switch, and the switch makes a copy. We'll see that when we get to multicast. Let's clean up my diagram. Broadcast. Send to everyone on the network. Different ways to implement it. What is it used for? Normally for distributing control or management information. You want to learn about the structure of the network. You want to know you want to know an IP address of someone, you want to know a MAC address where you know the IP address of a host. ARP uses broadcast. With ARP, Address Resolution Protocol, we want to know some MAC address. We don't know it, so we broadcast to everyone and saying, do you have this MAC? Do you have the MAC address for this IP? So when we're managing the network, learning about information, broadcast is commonly used. DHCP, ARP, you've seen broadcast being used. So let's move on. Go back. Unicast, one-to-one association between address and host. Send to one particular host. Broadcast, one-to-many association between address and hosts, where many is every host on the network. Multicast, one-to-many association between address and hosts, same as broadcast, but many in this case is a selection of the hosts, not all. So a group of the hosts are the destination in this case, a subset of all hosts. Example, if we want to send a packet from source host 4 to hosts 2 and 3, we could use potentially multicast, because we could send a packet to the router and then the router could use multicast to deliver to 2 and 3, not to 1. Broadcast is received by everyone on the subnet, multicast to a selection of hosts on the subnet. In fact, it's a more general form of broadcast. We could say broadcast is just multicast, where the selection of hosts is all of them. You see, broadcast send to everyone, multicast send to a selection of hosts. If we select every host, multicast becomes broadcast. It's more complex than broadcast though, if we want to send to a selection of hosts, because we need to somehow select those hosts. indicate who is in this group of destination hosts. So it requires extra management protocols for hosts to subscribe or join a destination group. And that's much more complex. We need some additional protocol. Both Layer 2 and Layer 3 protocols can have multicast. IP multicast is available. Ethernet has multicast. The simplest way to implement multicast in Ethernet, let's say, again, router 7 wants to send a packet to host 2 and 3 in this subnet. In the previous example, router 7 sent a packet to all hosts in the subnet. It used the destination FFF address. Let's clean up. Now router 7 wants to send to host 2 and 3. Creates an IP datagram. It can set the destination address of that datagram to a special multicast address. In the Internet Protocol addresses, we've seen that there's Unicast addresses, the address for a particular computer. We've seen special case broadcast addresses, this all ones address. There's also special case multicast addresses. And they're within the range, where do I say it? In a later slide I say, but it's within the range from memory 224 dot up to 239 dot whatever. That is, there's a range of IP addresses which are reserved for multicast, where one address represents many hosts. We have a one-to-many association. One IP address represents a group of hosts, not all, a subset of all of them. So if this IP datagram is set to a multicast address, I'm starting to mix real IP addresses with our A and B addresses. How do we deliver that to 2 and 3 over the LAN? Send it in an Ethernet frame and set the destination address to a multicast address. Similar in Ethernet, the MAC addresses have a special case multicast address. It's an address where the first byte, the last bit in the first byte is 1 from memory. That is a MAC address, 48 bits. The first 8 bits, if the last bit in the first 8 bits is a 1, then it indicates as a multicast Ethernet address, multicast MAC address. So there's a special case as well. Similar to in IP, the first decimal number is either 224 to 239. That's a multicast address. There's a similar structure for MAC addresses. It's the last bit in the first 8 bits is a 1, then it's a special multicast address. So we set that to one of these special multicast addresses. How do I write it? A MAC address, 48 bits, with a special pattern where there's a 1 here. It doesn't have to be all zeros. It can be something else. How do we implement multicast in our LAN? Where does router 7 send to if the destinations are 2 and 3? Where does router 7 send to if the destinations are 2 and 3? It's a multicast. It's an easy question. Where's the router going to send to?
Switch.
The switch. And how many copies of the packet is it going to send?
1.
If we implement multicast, it will send 1 copy to the switch. Here's our Ethernet frame. has a special destination multicast address, the router is only connected to the switch. It's the only place it can send a frame to. Sends to the switch. A simple way to implement multicast in LAN is to use broadcast. The switch sees that this is a special destination multicast address. Send a copy to everyone. Note that only 2 and 3 are in our destination group, but the switch sends a copy to everyone. Now the next step is that the receiving hosts check the destination address. If they are in the receiving group, they'll process the packet. 2 will receive, check the destination and process the packet. 3 will receive and process the packet. 1 will receive, 1 is not in the destination group and will discard the packet. So in this case, what's happened at the layer 2 level, we've used broadcast, and broadcast send to the switch, switch sends to everyone. Everyone receives a copy, but based on the destination addresses, only some hosts process that packet. The hosts which are in the destination group process that packet. In our example, 2 and 3 process it, host 1 discards it. Alternatively, the switch could implement some multicast mechanism and check, okay, 2 and 3 are within the group, only send copies to 2 and 3. But that requires some more complexity from the switch's perspective. The problem here that we've skipped over is how do we know which hosts are in the destination group? With broadcast, everyone should receive a copy. With multicast, only a selection of hosts. Which hosts? That's where we need some way to subscribe or join some group. We will see when we go through, we've got some slides later on IP multicast, so we'll have some more examples about multicast using the internet protocol. The basic approach is that if you want to subscribe to a group, you use a special protocol to subscribe to a group, tell the routers you're in that group, and then the routers will forward copies of the packet to you. But we'll cover that in some depth later. Multicast is useful if you want to implement TV over the internet. There's one TV station that creates the packets. They are the source. You have your TV at home using IP TV over the internet, IPTV. You turn on your TV and switch to some channel, channel 5. And when you switch to that channel, that means you subscribe to a particular multicast group. And 1,000 other people at the same time have subscribed to the group representing channel 5. What happens in the internet is that the TV station sends one copy of the packet, destination is channel 5, or the group that represents channel 5, and the routers deliver copies of that packet to all the hosts which are subscribed to that channel. So my host receives a copy of the packet and it displays the TV. The other people who are watching channel 5 also receive copies. Instead of sending to everyone on the internet, because not everyone is watching that channel at the same time, and instead of sending individual copies to every destination, multicast can be more efficient. But we'll return to multicast in the internet shortly. Useful for multimedia applications, like I said, streaming TV, streaming audio, when there are many users involved. Conferencing, collaboration applications, we have a group of users and they all want to see or receive the same content. So we've gone through 3 so far. We'll return to multicast. Unicast, broadcast, multicast. Last one, delivery mechanism, Anycast. we have a one-to-many association between address and hosts, same as broadcast and multicast. We have one special address which represents many hosts. In broadcast, many meant all hosts. In multicast, it means a selection of hosts. In anycast, it means any host in a group of hosts. Any of many. So similar to multicast, there are a group of hosts which are in the destination group. The source sends one copy of the packet. The idea in anycast is that the routers in the internet will deliver a copy of that packet to any of, or one of any of the hosts in that group. It's not a good example to show it, but let's say 2 and 3 are in the group, the destination group. 7 is the source. The network needs to deliver a copy of the packet sent by the source to any of 2 or 3. If it goes to 2, successful. If it goes to 3, successful. If it goes to both 2 and 3, successful. If it doesn't go to either of 2 and 3, unsuccessful. So, multicast, a copy must go to both 2 and 3. Anycast, any of them. We don't care which one. That's useful if you have applications where you need redundancy. That is, you have servers in the internet which are replicated in different locations. For redundancy, I want to send a packet that reaches any of those servers. I don't care which copy of the server, which replicated copy, just one of the servers. So I send the packet to a special anycast using anycast, and the network makes sure that one of those servers receives a copy. Which one, from the source's perspective, it doesn't care. DNS is one example, or advanced DNS mechanisms. With DNS, I send a query for given a domain name, tell me an IP address. I send it to a DNS server. But there are many DNS servers in the internet. With anycast, I send, and any DNS server can respond. And I'm happy if any, I don't care which one responds as long as the fastest response comes. So in some advanced implementations of DNS, anycast is used, especially at the top level DNS servers, the root DNS servers. We will not go through any example of how to implement it. It's a very special case. So we have 4 ways to deliver packets in a network: unicast, broadcast, multicast, anycast. Make sure you know the differences between them and the advantages and disadvantages. You can implement broadcast using unicast by sending one copy to everyone, but it can be inefficient. Before we go on to IP multicast in some depth, any questions on how they work, those 4 different mechanisms? This slide summarises them in some nice picture. Unicast, so the green computer is the source, the red ones are the destinations. Unicast, send to a particular destination. Broadcast, send to everyone in the network. Multicast, send to a selection of groups in the a selection of hosts in the network. Anycast, send to one of a selection of hosts. So there are multiple potential destinations, send to one, any one of them. Random, not necessarily random. How do you choose which one? It's up to the network to choose which one receives it. There may be some performance criteria, that is, the closest one, maybe the one that receives the message. With a DNS server, we have DNS servers across the internet. I want to reach any DNS server, then the IP routers can be configured to try to reach the closest DNS server, and that DNS server responds. So performance criteria may choose, but the concept is anyone. Could be random, could be on other criteria. Unicast is what we use every day. Broadcast, we've seen it in some special cases. You've seen it in labs in ARP and DHCP, uses broadcast. Multicast, not so common today, but used in some networks. We'll cover that in some depth. Anycast is the main application at the moment is in DNS servers. Not for my computer using Anycast, but the DNS servers which are what's called the Root DNS Service, which there's 13 Root DNS servers across the world which are all replicated, and they keep the information they're the root of the DNS hierarchy. There's a hierarchy of DNS servers. These are the top level ones, the most important ones. And Anycast can be used in that case. Let's look at multicast in a little bit more depth. IP multicast. Here's an example. We have a source host, some destination hosts, and some routers. So a simple internet here. In multicast, the routers, in multicast in the internet, the routers must be involved in delivering the packets. What example do I have? There are other hosts, they're not shown here, but imagine that attached to each router there are many hosts. This router there may be 20 different hosts attached. We're only showing the hosts which are part of the destination group. So in this case, with multicast in the internet, we have a single source, and some hosts in the internet join a group. In this example, these 5 hosts are part of group G1, group 1. We use a special IP address to identify a group. If we skip forward a few slides, I think the format is given. There is a special range of IP addresses for multicast, 224.000 up to 239.255. And within there, there's some other special cases. But each IP address, almost all IP addresses in this range, can be used to identify a group. In this example, 226.17.30.197 is one IP address which identifies a group of hosts. So going back to our initial example, when I say group G1, I mean some IP address that identifies that group. For example, this 226 address. And the source has an IP address, a normal Unicast IP address. For example, that's G1, and the source, S1 in the diagram, 72.13.6.3, some random IP address. That's a Unicast address, that's a multicast IP address. The idea in IP multicast is that you want to send as few packets as possible to reach all destinations. Assuming the routers know something about the hosts which are part of this group and have created routing tables that know how to reach members of the group, then how packets are forwarded through the network is that the source creates one copy of the packet. Source address S1, destination IP address G1. So an IP packet where this is the source address, this is the destination address. Just a normal IP datagram. Sends it to its local router. then the router has its routing tables configured to deal with multicast. So these routers now have special capabilities that they can participate in multicast routing, which means that, for example, if this is the first router R1, then it would have to have some routing table which says that to reach group 1, the destination group 1, there is a host directly attached, and also to reach group 1, send to, if this was R2 here, R1, R2, send to R2. If this is a special multicast routing table for router R1, if it's configured to say that to reach group 1, I need to send a copy to some host which is directly attached, and I need to also send a copy to R2. That means when the source sends an IP datagram, it reaches router R1, destination address G1, router looks up in its routing table and it sees it needs to send a copy of this packet to a host which is directly attached, this one. It needs to know who that host is. We don't give it a name there. So send a copy to this host. Why? Because this host is a member of the group. There may be other hosts attached as well. They don't need to receive a copy, just this one does. But also make a copy of this packet and send it on to router R2. R2 would receive a copy and its routing table needs to be configured to know I need to send one copy to this host, which is directly attached. I need to send one copy to this router R3 and another copy to this router down here, R5. And similar, R3 sends direct and we send on to R6, which then sends to these two hosts. So the routing tables in the routers need to be configured to handle multicast. How are they configured? There are now multicast routing protocols to configure these. That's where the complexity of multicast comes in. It makes life for routers more complex, and it makes routing more complex, and somehow the hosts need to tell the routers that they are part of the group. For example, this host would tell its router, I am in group G1. If this host, we don't have a name up there, but if it was called host H1, then this host, if it's in group 1, would tell the router, I am in group G1, and therefore the router can store in its routing table, group 1 includes H1. So when the router 1 receives this packet, it sends a copy to host 1. And similar, this router has told, router 2 has told router 1, I have some hosts which are in group G1. Therefore, if you receive a copy of a packet that is destined to G1, send a copy to R2. And that's how we get this entry. Router 1, when it receives a packet destined to G1, it knows it needs to send to R2. So somehow the hosts and then the routers need to tell the other routers where are the members of the group so that we can direct the packets in the right direction. If that works, if with multicast routing has been configured correctly, let's count how many packets were sent through the network. Source sends one packet. There's one. The router sends one to the host, plus onto router 2. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this simple example, 10 copies of that one packet were sent, and it reached 5 destinations. 10 copies of the same packet, and it reached all the destinations. That was using multicast. If we didn't have multicast, we had just unicast, how many copies of the packets do we need to send? Calculate it. Anyone got an answer? Someone's got 19. Anyone else? If we just have unicast in this case, we want to send from the source and reach those 5 hosts. 5, 19. Anyone else want to guess? How many copies are sent through the network? Not just by the source, across each link. Anyone else? 10, 5, 19? In multicast it was 10. The diagram up there. What about unicast? Anyone else? What do you think? 19? 19. 19 is correct. Let's see why. With unicast, the source needs to send a copy to the first host. So send to the router, assuming it's sent across the least hop path. Send to the router plus the host, there's 2 copies. 1, 2. Need to send to the third host, or the second host. 1, 2, 3, so 2 plus 3 is 5. 1, 2, 3, 4, another 4 is 9. We're looking at the total number of transmissions in the network. Why? Because the more packets we send to the network, to get one piece of data to the destinations, the larger the overhead of using the network is. We want to ideally send as few packets as possible to get the data to the destination. So we have 9, 1, 2, 3, 4, 5 is 14 plus another 5, 19. So we can think 19 transmissions in the network to get that one piece of data to 5 hosts using unicast. With multicast, we've reduced it down to 10. That's better because we only send 10 copies of the packet to get the same amount of data to the same destinations. Broadcast would be worse. Broadcast would be send to a router. Router sends on every link. All right. Although that's not even possible with the internet, but if we think we send on every link, then even if we had more hosts, they would receive copies. That would be even worse. So the benefit of multicast is that we can reduce the overhead in the transmissions, less transmissions in the network. The disadvantage is it's complex because somehow the routers need to know about where to send a copy of the packet. How did this router know to send copies in these 3 directions? How did this router know to send in this direction, not in this direction? Well, it must know that there are members of the group in this direction. And that's where you need routing protocols. This summarises what we just went through with the same example. There should be 5 blue boxes here, I think. But if you add up the blue rectangles, then I think you should get 19. This should be 5 here. If we use unicast, what's called, or simply multiple unicasting, to achieve the same goal as multicasting. With multicasting, a single packet is sent from the source, copies are made at multicast routers where necessary. So these routers must have special multicast capabilities. We'd call them multicast routers. In multiple unicasting, or just using Unicast, we can emulate multicast, try to achieve the same goal. The source uses Unicast to send a copy of the same packet to each destination. Simpler, it doesn't require the routers to support multicast protocols, but very inefficient. Channel 5 TV station is providing TV over the internet. Everyone in the world who wants to watch that channel subscribes to a multicast group, so the TV channel sends one packet for every part of the video that they're trying to send, and then the multicast routers deliver to all the people at that time in the world that have subscribed to the channel. As opposed to using multiple unicasts, using multicast can be much more efficient. We send fewer packets through the network. What do we need for this to work? IP multicast is an optional feature in the internet today. Hosts and routers to implement multicast need some extra capabilities. Most hosts and routers support multicast. That is, my host, the operating system supports it. It has the capabilities. Most new routers that companies buy support multicast, but many internet service providers have not enabled it. That is, they haven't turned on that capability in their routers, because it still requires a lot of complexity in the routing. Even though the capabilities are there, the routing protocols introduce extra overheads. And what's the benefit from the internet service provider from providing it? So in practice, it's not enabled in many networks. We need an IP address, so there's a range of IP addresses that are special multicast addresses. We'll see that in a moment. For multicast to work, we need these special IP addresses, multicast IP addresses. Routers must be notified which computers belong to which multicast group. In this one to work, these 5 hosts in the internet needed to notify the routers that they are in group G1. There are other hosts here, although not shown. So these ones must tell the router, I am in group G1. And there's a protocol in the internet called the Internet Group Management Protocol that does that for us, or allows the host to tell the routers which group it wants to join or subscribe. And the routers must be able to create their routing tables, like the simple example we had here, to forward the datagrams in the right direction. So we need special multicast routing protocols to do that. It's more complex than normal IP unicast forwarding, and the routing protocols are more complex, and there are different routing protocols. These are the names or the acronyms for some multicast routing protocols. So your router needs to support multicast forwarding and multicast routing, so that it can create the special routing tables and forward packets to multiple destinations. So those 3 components, the IP multicast address, the group management protocol, and the routing protocols. Let's look at them. Multicast address, there's a special range of IP addresses reserved for multicast. This is the range, 224 up to 239. Within that range, there are again some special ones reserved for special multicast groups. Others are available, or most of them are available for any multicast group. Where a single IP multicast address identifies a group of computers. Multicast addresses only used as a destination, never a source. the source always uses its normal IP address. Here's an example. Here's a source with a normal IP address. And here are 3 hosts with normal IP addresses, but they're also members of a multicast group. So every host still has its normal IP address for normal unicast delivery, but a host can join a multicast group where that group is identified by an IP multicast address. If you join the group, if IP forwarding and routing is working correctly, then when this source sends a packet destined to this multicast address, everyone within the group should receive a copy. That's the goal. How do you join a group? There's a protocol called Igmp, Internet Group Management Protocol. In theory, any host can send a datagram to an IP multicast address. Coming back to this example, all of these hosts have IP addresses. Here's a multicast group address. Any host can send an IP datagram, a normal IP datagram, where this is the destination address. And in theory, if this host sends to this destination address, the 3 group members will receive a copy. If this host sends to the same multicast group address, these 3 will receive a copy. In practice, routers will prevent that from happening. Because if we allowed that to happen, it means that, again, same with broadcasting the internet. If I know a multicast group address, I can send a packet to it. Everyone in the internet on that group will receive a copy. For security reasons, we don't want to allow that. We usually only want to allow a particular source to send to that group address. Otherwise, once someone knows your group address, anyone in the world can send you packets, and you can start to flood those destinations. That is, easily send many packets through the internet. Normally routers will block that. The host registered with the multicast address will receive the datagram. That is, we say that those hosts are in the same multicast group. Igmp allows hosts to join and leave a group, to subscribe to a group and to leave that group. How does it work? When a host wants to join a group, it sends an Igmp join message to its local multicast router saying, I want to join the group 226.1730.197. I want to join the group. And then it's up to that multicast router to inform other routers so that when the source sends a packet, this one will receive a copy. So we join a group by sending to our local multicast router, and then the routing protocols are updated so that when a source sends a copy of the packet, this one should receive a copy. Sorry. So a host joins a group using Igmp. Similar, it can leave a group. Send a leave message to your local router. And again, that local multicast router needs to update the other routers to say that you no longer need to send copies in this direction. So each host, we can say, has a local multicast router. In the same way that each host normally has a default router, the local router. You join to your local multicast router, and the local multicast routers periodically check with the group members and see if they're still alive. They still want to be part of the group. That is, I join the group, 5 minutes later the router may send a periodic message saying, are you still in the group? If I want to still be in the group, I'll respond. If not, if I don't respond, the router may remove me from the group. That's in case a computer fails, for example, or turns off. so that we can remove it from a group. So a host joins a group by sending a join message to the local multicast router. That local multicast router propagates that information to other multicast routers in the internet and keeps track of the group members. The advantage of this approach is that the source doesn't need to know who's in the group. This source, just a normal source on the internet, sends one packet. If there are 3 members in the group, with IP multicasting, all 3 members will receive a copy. The source doesn't know if there's 3 members. If there are 10,000 members in the group, all across the internet, the source just sends one copy and it's delivered to all 10,000. The source doesn't care how many members are in the group. It doesn't need to know whether the group members change or not. So it's very simple from the source's perspective. It's up to the routers to manage the group membership. The last part, so we need multicast addresses, group management, and we need forwarding and routing to support multicast. When we send a datagram to some multicast address, we send to our local multicast router, which then needs to forward it through the internet to reach all the group members. It is sent to the next router based on routing tables until we reach all the group members. So we need some routing protocols to communicate between the routers to work out what is the shortest path from source to all the destinations. In going back to our first example, look at the paths from source to the 5 destinations. It forms a tree where the source is the root of the tree and the destinations are the leaves. So the best paths to the destinations form a tree like this. How was that tree discovered? Using a multicast routing protocol. Why didn't we send this direction? Because the routing protocol found that this direction was the best path, using whatever metrics we choose for a routing protocol. Why not send out here? Because there are no hosts in the group out here. So a routing protocol needs to discover this tree from source to all destinations, and the best tree. Another tree from source to the destinations could go in this direction, but it may not be the best one. The problem is, every time a host joins or leaves a group, the tree may change. Let's say, if you can see the tree, in this case, here's the source. It goes where the packets are going. If these 2 hosts leave the group, then there's no need to send a packet here. So we need to update the routing tables such that if these 2 hosts leave the group, the tree just becomes sent to these 3 hosts. That is, these 2 hosts tell the router, I want to leave the group. This one then needs to know to tell this router, I have no more hosts that are in the group G1. And this one needs to decide to tell this one, I have no more hosts in group G1. But what if there's another host here that joins the group? Then now the tree must go in this direction and include this host. So it becomes very complex because every time a host leaves or joins a group, potentially the tree going from source to all destination changes. The best paths change. So the routing protocols become very complex and a lot of overhead to maintain them, compared to normal unicast routing. There are several routing protocols available for multicast, built for the purpose. Trees are used to define the least cost path from source to all destinations. IP multicast forwarding and routing is much harder than unicast forwarding and routing, because the least cost routes may change rapidly as nodes leave and join the groups, and there are no acknowledgements. Same in broadcast. If I send a message to everyone in the group and everyone acknowledges, then I receive many ACKs and overflow my node. The same problem in multicast. If I send a message to 10,000 group members, if they all sent back an acknowledgement, I'd receive 10,000 acknowledgements for every one packet I send. That would overflow my node. So normally in multicast, we don't have ACKs. Means we have unreliable delivery. We don't know if the data gets there. So that's another complexity compared to the reliable datagram, reliable protocols. So multicast is much harder than unicast in practice. And that's one of the reasons it's not enabled by some of the internet service providers. That finishes on the topics for today on how do we deliver packets through the internet using unicast, broadcast, multicast, and also anycast.